as I said, this lesson goes through the three methods very carefully, does an example of each, but also talks about how do I decide which method I'm going to use? Because I know which method I want to use. Maybe it comes to which can I use? What's going to work here? So all the way back to the start of this. In fact, this is an example we did in previous chapters. Find the volume of a solid generated by revolving the region y equals x cubed, bounded by y equals x cubed, y equals 0, and x equals 2, about the x-axis. You need a little graph here. And when you're doing these, they mostly give you graphs that are pretty easy to come up with. That is, even if you didn't know what y equals x cubed looked like, it wouldn't take you long to go, okay, well, if x equals 0, 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. You know, not a particularly tough graph to come up with. So I'm going to draw that on there. And when I draw it in pencil, that graph I draw pretty thickly. I really draw that on. I'm going to show you how to draw these. How I found I can draw them so I can see what's going on. When I do the other side, I'm going to use a different color just to see it. So y equals x cubed, y equals 0. So that's y equals 0 right along there. So I'm just going to really dot that along there to go, that's the bottom of this solid. And x equals 2. So that's right there. And you'll see in a second why I'm putting just dotted lines on those other two to go, that's what we're talking about here. Then I'm going to do that weird shading. Yeah, that highlight shading of this. That color's good, right? You said yesterday that color, you can just barely see it. And when I'm doing it on my page, I just draw a few of those little very light lines to go, there's the solid. Can you visualize it now? The solid's going to come around the x-axis, and I'm going to have this thing here. So what I do is then I go on very light pencil, so I'll use maybe I'll use that same color I'm using there. And I go 1, 1. No, you're not going to see that, are you? If I go here, no, here. We'll try orange, okay? 1, 1. And the idea is that you can just barely see that. I'll sort of dot it on my own. There's the other side of it. And now I can maybe really visualize this weird looking solid. It'll almost look like a cymbal, from a band, this part here. So I'm going to highlight that in there. There's the visualization. Yeah, who am I talking to here at this part of the lesson? People who are a little behind, not sure how to do any of these. Yeah, this is how you manage the picture so you can see what's going on. This said use circular cross sections. So what they mean by that is, if I draw a little washer here, I'm going to go in blue here, not a washer, a disc like that, and like that. Can you see that little disc in there? As this thing wraps around, it's made up of these individual slices of bologna. My prof who taught this always talked about he likes slices of bologna. I don't know if he liked bologna sandwiches or not, but he certainly acted like he did. He talked about, hey, you're just doing these little slices of bologna. And then he was good at shading it in a little bit so you can see it's not just a flat disc, it's a little slice of bologna. And that little slice of bologna being width this way, I already know this is a dx question. I used to write this off to the side. I already know we're talking dx because the width of the bologna is dx. It's an x width in there. That really helps to decide, are we doing dx or dy? By looking at the width. Once you have that picture, now I'm talking to people who are pretty good at these. Once you have that picture, you're in the clear on circular cross sections. Slices of bologna is nice. Integral from A to B of the area times the width of the slice of bologna. That's it. Yeah, pretty straightforward. In this case, it's circular cross sections, so maybe that's not even the first step. Maybe this is the first step. And I made the mistake last night. I was doing one of these at home, and I made the mistake I always make is I forget to square it, and now I know why I write the radius in the separate brackets. It's like, Rob, put the radius in there and then square it afterwards, because you can get confused if there's squareds or cubed in the radius, and you have to square that as well. Maybe you ran into that where it was like a square root squared and you missed the squared. That's pizza time in these questions. I don't think these are particularly difficult compared to the other ones. That's order pizza time. Like, I got that formula down. I know I'm doing circular cross sections. I got the picture. The rest is a walk in the park. Volume equals, volume equals. Okay, volume equals. Get that pi out front. Don't let that mess you up. Integral a to b. I look over here at the dx. That helps me decide what the x values are, and my picture does too, 0 to 2. You see, I just went dotted line to go, this is where this symbol ends. Does it look like a symbol, music people? You see what I'm talking about? It's one side of the... Right. Volume equals 0 to 2. Now the radius, careful. Put the radius in there. What's the radius? The radius will be the y value anywhere along the way. Y equals, well, I already forget, what was the equation of this thing? X cubed. That's the radius each time. Nicely, when you rotate around the x-axis, the y value is the radius of the slice of bologna. Yeah? If you were cutting bologna down at each one here, the y value would be how much bologna you're getting in each slice. More and more bologna as we go.
So since we're rotating that equation, the equation itself will be half of the total shape.
Yes. The x cubed is half of the total shape. That works out good here. You're like, do I have to go top to bottom? And then? No. You're just going, because the radius is just here, you just have to go across like this, 0 to 2, and use that radius, which is half the whole height of the symbol. Yeah. So the radius here is the x cubed squared. Now, I don't know about you. That's where I usually make my mistake. Once I get the x cubed, my brain goes, okay, subbed in the x cubed, I'm done. And I forget to square it afterwards. That's my common mistake in these. Well, the rest then is really straightforward. I'm not going to take the integral yet. I'm a patient integral person. I make sure the integrand is exactly what I want before I take that integral. It's as tied up as I can do it, because taking integrals, taking antiderivatives is very, very difficult. It's the most difficult thing we do. But I'm home free now here, I think. Pi antiderivative will be 1/7 x to the 7th from 0 to 2. And then volume equals. I'm going to do both brackets here, but lots of times in volume, the second bracket, you're just subbing in 0. Nothing comes from that anyways. So that's nice, but I'll do both here just to show it this one time. So this is 1/7, 2 to the 7th. And this is, there'll be another bracket, 1/7 times 0 to the 7th. If you're at the point where you're like, when that 0 is there and you can see subbing in 0 doesn't do anything, if you totally leave that out, that is totally fine and maybe less confusing, actually. And so what I get here is volume equals 2 to the 7th. 2, 4, 8, 16, 32, 64. I get 128 pi over 7. Those are supposed to be the easy ones by now. Yeah? When you get circular cross-section, you're like, oh yeah, area, pi r squared, y value, boom. We like those. Okay? If it's not, now's the time for questions. Do you have questions about anything I did in that procedure there?
So our y value is...
Yeah. And you know what? You say, well, why couldn't it be rotated up here? If it was rotated over an axis out here, we just move it down here to the x-axis to make our life easier. Why would we do it rotated along some other axis unless we had to for some reason? And the bundt cake was an example of that. The bundt cake forced us into that situation. Yeah.
If we were doing y, then our x value would be 30.
Right.
Okay.
Absolutely. Absolutely it would be. Other questions here? Okay, we're 1 for 6 then. Do you need more time here? Now we'll do the exact same question using cylindrical shells. Establishing a couple of things. How is it different? And why would we choose it? And I'll give it away right now. I don't think you would choose cylindrical shells for this question unless you were absolutely forced to by the nature of the question. I'm just trying to show off how does it work. Okay? So exact same question, so I need the exact same picture. 0, 1, and 8. And then on the other side I'm going to try green this time and see if that does what I want, which is you can barely see it. When you're drawing it with your pencil, you can easily draw it lighter. Can you see the green barely, Heather? Is it just barely see the green? Okay. To do it with cylindrical shells, the big decision is, and this is where the coloring in of this thing becomes important, to go, where are these shells? That's the challenge of the shells. There's the volume I want. And if I put shells this way, vertically, they're going to do volumes that I don't want to do. They're going to go over on this part of it. It's got to be shells this way. The slice has got to be out of here. Picture the bowl. The bowl was actually the best of the examples the other day, better than the bundt cake in some ways. The bowl was sideways like this, and I was trying to do a bunch of these. So they're this way to get those volumes. So that's the challenge of the shells. And drawing the shell on, oh boy, that is not simple. You gotta almost have it already visualized in your head. But maybe I can draw a little shell in here. Little shell in here, from there out to there. Can you see the little tiny shell that I got there? And then, this is the part I'm not good at, that I don't know how that prof used to do it on the chalkboard. Just a little width of the shell on there. Do you see that little width on there? The shell has some kind of width to it. And that width on there immediately tells me, oh, it's dy. Because the widths are dy widths. That to me is the toughest part, deciding whether we're dx or dy. Because it maps everything I'm going to do next once I know whether we're going to be dx or dy. And drawing the little shell, it goes, where would the width of the shell be? The width of the shell would be this way, which would be in the y direction, and so I'm dy. That's one of the big aha moments of the lesson. Like, how do I decide between dx and dy? Get a little tiny diagram of the shell in there so you know which way the shell is. So then I go volume integral a to b, this time 2 pi rh dy. Now, in the examples I did yesterday and in the textbook, they go radius of shell in words, height of shell. So if you're having trouble with shells, don't write r and h, write radius of shell, height of shell, and think it through. So if we're dy, that helps me make a lot of decisions. If I'm dy, what are the limits of integration if I'm doing it with respect to y? 0 and 8 this time, because I'm going in the y direction. That changes my limits of integration usually. Oh, 2 pi. Oh, did I leave enough room? I'll sneak the 2 pi out there. I don't want any part of the 2 pi in these calculations. Radius of each shell is just the y value. As it goes along here, it's just the y value along there. So that's nice. The picture helps me see that. Then the height of the shell. This is the hard part. The top of the shell is always at 2. It's always going to be the top of the bowl from the demo I did yesterday. So this is going to be 2, subtract the x. And I'm going to write that in there. Because when I was doing them, I can remember way back when I'd write an x in there going, it's the x value. That's not going to work for my integral. I got to do dy's. So it's just x there so I can think for a second. Just stop for a second and go, it's the x value. Then I go over here and finally write on here, this is, what was it, y equals x cubed?
Yeah.
Cube root y, which is y to the 1/3. That's just getting ready for the integral. The cube root y is correct, but it's y to the 1/3. Then I go back over here and go, no, come on now. You can't have x. You might want x, but you can't have it. Y to the 1/3. And here comes the most important sentence of the day, which I'm going to say several times today. Because I could solve for the y value, then the cylindrical shell method is going to work. Yeah? Because I could solve for the y value. Yeah? This will come up with washers as well. Oh, well, the rest of it is not easy, but it's not the same kind of thinking. This is now integration that we got to do here. So again, I stick to what I said. Get the nicest possible integrand that I can. And I think that's the best I can do. I've changed the cube root to y to the 1/3. I've multiplied that y in to make things as easy as I can. Now antiderivative. Let's see. 2y is, that's an easy one. Y squared. Yeah, after you've done a bunch of integrals, things like 2y are nice when they pop up. Y to the 4/3 is not easy at all. Increase the power by 1 up to 7/3. So then to get rid of that 7/3 in the derivative, I need a 3/7 out here. That's awkward. Take a look at that for a second and see if that's okay. Because that's the kind of thing that just spins by now. Like 2 weeks ago, that was difficult. Or 3 weeks ago, that was really difficult. And now it's like, oh yeah, just play around with the coefficients and get it right. 4/3 plus 3/3 is 7/3 if I'm doing the antiderivative. And a 7/3 coming out front to multiply needs a 3/7 to turn it back to a -1. Yeah? Now I'm ready. Now I'm going to leave out the zeros this time, okay? The second bracket is going to be all zeros, so I don't care about the second bracket anymore. Yeah. Oh, no, this isn't ready. No. Hang on a second. You'd find out if you tried to do it. Well, maybe you're calculator reliant. Maybe you're so reliant in your calculator, you just punched it into this. But if you don't want to be calculator reliant, we need 3/7. This is cube root of y to the power of 7. That's really what we should use if we were trying to survive without our calculator. Was at U of T yesterday, and they had a sign there that said, which calculator are you allowed on your exam? And it said, check with your prof. Yeah, so that's something that you have to find out right off the start of the course. What calculator am I allowed for the exam? And then make sure you can do the questions with only that calculator. Anyways, now I'm ready. I'm skipping the subbing in zero stuff. I'm going to sub in, oh, where is it? 8. I lost my limits there. And then I wrote them the wrong way. 0 and 8. Okay. 8 squared minus 3/7 cube root of 8 to the power of 7. Volume equals 2 pi. This is a 64. Cube root of 8 is 2. The power of 7 is 128 times 3 is 384. Let me check that again in my head. Cube root of 8 is 2. To the power of 7 is 2, 4, 8, 16, 32, 64, 128. Times 3 is 384. So if I wanted to do this without my calculator, I'd need 7 times 64 is 420 and 448 over 7. Oh, I'm a little nervous. If it's going to come out right, let's see. I'm going to try and land it in my head here. You wouldn't. You get your calculator to help you all the way. Even a simple calculator would help you to do 7 times 64. Even if you're only allowed a really simple calculator in an exam, you could still manage your way through this. 48 and 16 more is 64 over 7. And I get 128 pi over 7. My old brain still can't remember whether that's the same as I got in the previous one. Is it? Well, that's good. Yeah? So, a bunch of things to say about this. The first is this method works. Got the same answer. The second is, would you do this question with cylindrical shells if you had any choice in the world? And the answer is no. Next, for you future teachers, then why do this example? Why do I do this example with that one? Is because it's a familiar example. We can figure out how to do the method in a situation we feel safe with so that we're ready for tougher questions. To teach a new method on a new geometry, that's too challenging for students usually. You want to teach a new method on familiar geometry, then go new method, new geometry. That's frustrating for students, so make sure you explain it to them. That's what we're doing. I would never do this way, but I could. Getting ready for later examples. Okay? Any questions about that one? We're 2 for 6. The good news is 2 of the next 4 are not too bad. Question? Yeah. Because the shells are this way, yes, then their widths are right there. The width of each shell, and that's a dy. It's this way. So you need to know which way those shells are going before you decide dx dy. The good news is, once you decide if it's dx dy, and that's why I wrote the little dy over here, it's just my brain going, okay, dy's, that helps me think a lot of things through. It helps me think through the limits of integration. I know I need y's in here, so remember when I wrote x there, I'm like, I know it's not right. Sorry, it's right. The x is right, but it's not usable. I've got to get over to y's eventually. Yeah, good? In here, the little slices of bologna were this way, and so the little widths were dx's, so I knew it was going to be dx. One of the main parts of today's lesson is to go, how do I decide? And this is what this is doing. Other questions for that one? More time? Washer cross section. I like washer cross sections. You know, like, what is it from Goldilocks and the Three Bears? You know, like, discs are too easy. Cylindrical shells are too hard. Washers are just right. You know, just a little bit difficult, but not too bad. And I like the pictures here, too. Is this a bad graph? Of this one?
Yeah, just like the measurement.
Yeah, okay. I think you need to see this at least once with square root. Square root does something you don't expect. I'm first going to find the volume of the solid generated by y equals root x, and below by y equals x. So let me draw on y equals x. I'm going to choose orange. I don't want the colors to overtake the picture here. Here's y equals x. And I'm going to hand draw them, because I think a lot of times you won't necessarily do this on graph paper. You're just hand drawing them to get the feel. But I want you to get your calculator for a second, and let's say we didn't know anything about square root of x. Like, I don't even know what this thing looks like at all, and I'm going to do it in pink. And we'll do the square root of each one so that you find out what square root does here, because it says y equals root x is above. But that's hard to picture if you never really broke down what happens to root x between 0 and 1. So I'm going to do square root of 0.2. And I get 0.44. Look how fast the square root function jumps up. And that makes it above here. Then square root of 0.4. My calculator wants to make it into this crazy root, but okay. 0.63. See how far up square root is? Far enough to make the gap here and be the above function here. I sort of have enough there now. You can do the 0.6 and 0.8 to get the feel for it, but basically square root really jumps up right off the bat, and then so I get this shape right there. Find the volume of the solid generated by revolving the region bounded above by y equals root x, got it, below by y equals x, about the y-axis, so it's going this way. So let me get the other side of this thing going here.
So it's probably
Where's the negative 1, 1? So when I spin it about, I'll get this on this side, and I'm drawing those dotted because for me that helps to get a picture of what's happening here. There it is. And it told us to do it by washers. It said go ahead and do washers. So I don't have to make the decision here. I'm going to do 2 in a row, and then we decide why we would do one over the other, right? With washers. Let me draw the washer in here. I tried to leave a color available to me. When I'm drawing them on my page, I just draw these sort of light, and then the washer I draw dark enough that I can really see what the washer looks like. Here's my washer. Let's see how I do. Start with the inner. Dotted in behind, like that. And then I do the outer. Dot it in behind like that. Can you see the little washer in there when I do it like that? Yeah, there's the washer. I don't even know what a washer is. Washer is just an inside-outside circle like that. You know, way back to grade 9, we made you do washers in preparation for this someday. You know, I'm going to try and color that washer in for you with that. It's like a makeup color, isn't it? Isn't that like a foundation? A little foundation there? Am I using the right words? Do I have any idea what I'm talking about? Lana's like, no, not really, but you know, it's okay. There's the once I have the washer, me personally, I'm at the point with washers where I'm like, okay, I can order pizza now. I can see the washer now. Everything else is going to be fine. But I will do that thing that prof was so good at, was giving me a little width on the washer. Yeah, just a little depth to the washer. He was great at drawing them. I'm getting there. It's like a little slice of bologna. Yeah? But it's got a hole cut in the middle. Yeah? It's like a donut almost. That width tells me we're talking dy here. Because the widths are dy in this particular question. So here's the washer formula. Volume equals pi integral a to b pi big circle minus little circle. And I've decided I'm going dy's here. Take a look at the little, there's the washer, imagine again, I'm giving you slices of bologna, but the center is cut out of the slices of the bologna. Yeah? I don't know why that would ever happen. I'm trying to picture a situation where this actually happens. Does any bologna come with a center cut through it? No. Okay. Little slabs of bologna, and your sandwich has got a little hole in the middle for ketchup, so you can put a little ketchup in the middle of your sandwich. All right? And the slice of bologna, its width would be here. So each of those widths is a dy as you go up here. It's not a dx going this way, it's a dy going that way. Yeah. So, volume equals pi out front, 0 to 1. In this particular case, 0 to 1 was the limits either way, whether you're going to go dx or dy. Big R squared. Okay. That's over here. That's the outer. This is y equals x. This is y equals root x. The big radius is y equals x. Do I want the x or do I want the y? The good news is y equals x. But do I want x or y? Why? Because the dy tells you. That dy is so important. It tells you which one are you looking for here. So the outer is y. I'm going to put it in brackets and put the squared outside to go, because that's my fatal error here, is forgetting to square the radius. The radius here is y. The outer radius is y, and I'm squaring that. Minus the inner radius. What's the inner radius? It would be root x. It would be root x. That is correct. It is absolutely root x. And yet, I can't use it. Yeah? So up here, I write it right up here. I go y squared equals x. Which one do I want? I want the one that's y's. So this is minus y squared. Squared. I always forget the extra squared. Always. Not always. I'm getting better. But that's my fatal mistake. Well, maybe you got to get here before you're ordering your pizza, because this is now, hopefully, you're in the clear now. I'll write the rest of the steps and then I'll pause for questions. Integral 0 to 1 y to the fourth minus, sorry, not y to the fourth. Get ahead of myself. Look at that. Y squared minus y to the fourth dy. Volume equals pi. Antiderivatives 1/3 y cubed minus 1/5 y to the fifth from 0 to 1. Ignore the 0 bracket. When I sub in 1, I get 1/3 minus 1/5. Let's see. That's 5/15 minus 3/15, 2 pi over 15. Now I pause a long time for questions. Because you might have questions on the geometry, the picture, the integral, the dy's.
What would this look like if we were measuring by dx?
dx's wouldn't work because your washers would be this way, vertically, and you'd be measuring rotated around the x-axis. And some people start making rules. The textbook definitely starts making rules. It says if you're rotating around the y-axis, your washers will be horizontal, making your widths vertical, and you're using dy's. And so you can memorize those things. I don't like doing it. When I start memorizing stuff like that, I start going, do I get what's going on here? Or am I just memorizing? Am I going to remember this come exam time? Am I going to remember it next semester when this pops up in an example? I like just thinking them through, but you can definitely start making rules if you want. As soon as it says about the y-axis for a washer question, you know that the washer is going to be this way and it's a dy. Yes, so you can make your own connections for whatever helps you understand it. Me, I just like drawing them every time and not being surprised, but knowing that I can figure it out with whatever's coming up. Other questions about the washer method for this one? More time? Okay, exact same question using cylindrical shells. Give me a second to draw this thing. I like the colors I went with last time. What did I go with? Orange low, pink high. All right. Orange. And then pink. We've learned our lesson about square root. Square root jumps up a lot before it levels back out to 1 there. So there's the left side, but we're rotating around the y-axis. So the other side of this thing is, there's y equals x. And then this thing really jumps up like that. I've tried to make it as symmetrical. Oh! I tried to make it as symmetrical looking as I could there. Because obviously it's completely symmetrical. It's just rotated around. There. Now, the cylindrical shells have to go this way if we're rotated around the y-axis. Shells this way would introduce a bunch of stuff I don't want. A bunch of pieces I don't want if you put them horizontal. That's why the picture's so good, and that's why the coloring in is so good. I don't want to color in this time. I don't want to get this I got to be able to see the shells that I'm going to make here. So here's the individual shells. I'll try and make one big enough that you can really see it. There's one shell right. Oh, I don't like, that wasn't circular enough. It's not going to be a very good visualization if I do it like that. More circular on the back of the shell there. And then the upper part of the shell, I have to go up. Maybe you're better at drawing them. I got to go straight up. And then there's the front of the shell. There's the back of the shell. There's the little shell each time. And then just a little width to the shell. Just a little width to the shell, because that tells me that when I do the width of the shell, it's going to be a dx. And you can memorize some rules going, oh, if the shells are vertical, then the integral's got to be dx's. Yeah, you can do all that as you practice them. Me personally, I like drawing the little width on it to go, I can totally picture where it was. The little pieces right there. So for cylindrical shells, where volume equals integral a to b, 2 pi, radius of the shell, height of the shell, and I've decided I'm going as a dx. So I get volume equals 2 pi, integral 0 to 1. Radius of the shell is the x value. Is that good? Dx, x value? Yes, it is good. Whew! That's a big moment. Then height of the shell. This is hard. I'll write on the two equations here in the right colors. This was y equals root x. And this is y equals x. We're going to need somebody right on the case here to figure out how I'm going to find the height of each of those shells. I don't know. Maybe it's hard. Maybe it's not. I'll get ready. Back in blue with the height of the shell right in there. It's the end of the difficulty of shell questions once you get the height of the shell. Jacob, what do you like here?
Would it be root x minus x?
Yeah. The top y value, subtract the bottom y value. That doesn't always happen with shells. Sometimes the top y value is just some number, or the bottom number is some number. But the shell's caught between two graphs this time. Then I'm in the home stretch. Volume equals 2 pi. Get your integrand in better shape here. X to the 3/2 minus x squared. Maybe you've got a question about that step that you want to ask. I don't know, but I'll continue on. Volume equals 2 pi 2/5 x to the 5/2. Maybe you have questions about that. I'm glad to answer them. 1/3 x cubed. This is from 0 to 1. 0 to 1 is really nice, because all I get out of this is 2/5 and 1/3. Boy, nice things happen there. Incidentally, if you show up next year at university and they're like, no calculator on the exam, that's a bit of a relief sometimes. We were happier. When the prof said no calculator, we're like, okay, the numbers are going to be 1s and 0s and 2s. You know, like, we're not going to have to get carried away. Prof shows up and says, I know my astrophysics prof in year 3. Oh, you can bring any calculator you want. That scared us out of our minds. We're like, holy crap, what's going to be on this exam if he lets us use any calculator we want? So don't be freaked out by that. That's fine. 2/5 minus 1/3. Oh, I can do 2/5 minus 1/3. Okay, 15ths. 6/15 minus 5/15 is 1/15, and so I get 2 pi over 15. Oh, was it the same? Does cylindrical shells work? Yes, it was the same. Of course it was the same. Cylindrical shells work. Probably, though, again, you're like, I am not using cylindrical shells unless you force me. Yeah? Washer was way better here. Easier to visualize, less mathematics. And again, we only practiced it on these, so we're like, okay, similar geometry gives myself a chance at landing this thing in a familiar situation before I move on to other questions. Do you have questions about that one? Zen, is it a question? Your hand can't seem to decide. Your hand's like, what question?
You know how to draw the cylinder, basically like where the stripes pass, and then like
The shell's got to be, all the shell's got to be inside the shape here. It's got to be, you're using these little slices of paper to add up the whole volume, which seems impossible, but maybe we've learned it's not impossible to break things into little pieces. So those little shells all have to be inside the shape. So when I put this shell here, and I might have chosen the perfect shell here, yeah, that's inside there. If I had gone this way, I'm introducing a bunch of stuff that isn't in the volume. So the picture and that little shading I do is important to try and visualize where these shells are. Easy? No. This is from the end of Calculus 2 in university. This is this time next year. You're a year before you get back to this stuff again in university. Maybe. Some profs are different. They go, no, let's do this now. Let's do, you can change the order of things here a little bit. Questions here? More time? 2 more to go if your brain is bleeding. Choosing the best method. So after all that, how do we choose? How do we decide? Well, here's how we decide. We try to do circular cross sections. We try to do washers. I'm not sure in university that I ever had a decision-making method. I would go ahead and try and do washers, and if it didn't work out, I'd go, okay, I guess I got to do this one by shells. But anyways, let's talk about it a little bit so that maybe we have a decision-making structure. Sometimes one method of finding volume generated by rotation is highly preferable over the other. For each of the following examples, state which method, cross sections, or cylindrical shells should be used to determine the volume of the described solid. Set up a corresponding definite integral, but do not evaluate it. Okay, so we're going to leave the integrals out of this. This is just decision-making. We'll make out the integral and we'll go, okay, hopefully we can do the integration on our own. The solid generated by revolving the shaded region shown below about the x-axis. So I'm going to lightly draw in green the other side of this thing. If it's revolved around the x-axis, let's see how I do and see if it looks symmetrical when I'm done. Is it too wide? Derek likes it? This is the other side of this thing there, okay? Sort of looks like a shark, does it? Baby shark, doo. Okay. Oh, now you're stuck with that all day, eh? Oh, thank you, Mr. Top. All right. So if you're going to use my way of thinking this through as going, can I please use washers? Please. Please tell me washers are going to work. In fact, by this point in the lesson, you might be like, just do washers. Washers works. This one, washers, doesn't work, and I'm going to find out how come. I'm going to draw the washer on there in pink, and I got to erase in a second because it's not going to work. There's a candidate to be the washer. How'd I do on the picture? Decent. Enough to go, there's a washer. If I'm going to do this, I'm going to have to take this y value and subtract that y value. Can I get a y equals equation out of this? Not in any reasonable fashion. I'll tell you there is a way, but it's like 2.5 pages of algebra to try and solve for y here. It's a complete nightmare. So washers is out because I can't solve for the y values. First moment where you're like, oh. Yeah, and you can see why I use this method. My decision-making method is, let me try washers. I draw a washer and I go, can I solve for the 2 y values involved? No, I can't. Washers is out. My decision is made. I'm stuck with cylindrical shells. I erase that whole thing. Shells is where it's at. I never did mention circular cross sections because I hope you're looking at that going, okay, there's no way it's circular cross sections. There's no way it's little slices of bologna. It's not nearly that simple. Now, if it's going to be a shell, let me get a shell out here. and try and show why the shell has to be horizontal here. If I put the shell this way, do you see how that cuts through and gets stuff I don't want? There, that shell can stay inside my little bundt cake the whole time. Well, I'm seeing some nodding there where it's like, oh, maybe now I can decide where the shell goes. Yeah, there is the shell there. So let me draw a shell on there. I need the washer and then all the way down. Okay, here we go. Shell. 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 Hopefully you're better at it than me. You don't actually need a super diagram here. You just need to be able to see where this thing is so you can decide where its radius and height is. Okay. Is it dx or dy? Just draw a little tiny width on the shell to go. There's the width of the shell all the way on. I'm not wearing my rubber bands. You know those bands? Anybody wearing one? Who's got a band on? Oh, you do have. Can I borrow one? You got a thing where it's like, no, I never take them off, or got any weird stuff like that? But he doesn't take them off. Do you see the width of the shell there? In his little band? There's the width there. So if this was the shell right here, can you see the width there? So the width is this way. It's a dy width. It's a difference in y in its width. That's pretty good. Almost choreographed there. dy. Once I know it's dy, then I can relax. Me personally, once I know it's dy, I can do the rest of the algebra, no problem. So here's the integral. Integral a to b, 2 pi rh, and I decided it was dy, which makes me very happy once I know it's dy. So, now that I know it's dy, the limits of integration are easy. Actually, I don't even know what limits we'd use for x. I don't know how far this thing goes out, so that was a hint in the question too. I don't have the x values here. 2 pi out front. Integral 0 to 1. Radius of each individual shell is just the y value of the shell. The height of each individual shell is this x value out here. So it's 12 y squared minus y cubed. And just to make it clear that we do subtract, I'm subtracting a 0 there, because the bottom of the shell is at y value 0 every time here. Not like when Jacob bailed us out with subtracting the two y values. I do subtract the two y values. Sorry, the two x values here. I do subtract the two x values, but this one is x value 0, so it makes it slightly easier. I'll just tidy up that thing a little bit, but this one did not ask me to evaluate. It just said set up the integral. We do that from time to time on an exam or a test. As I go, let's not waste time finding this integral. Just show me you can make up the integral. y12 y squared minus y cubed. No more minus 0 needed.
Why
Yeah.
do you subtract 0? Is that because that's like
The lower bound. If this was another curve, see in the previous question, this shell had, the bottom wasn't 0, it was another y value.
the axis?
But here the axis is the bottom of the shell, so I put the minus 0 in there to go, yes, we always minus the bottom. It's just a lot of times we're minusing 0. Yeah. Question? Oh, yeah. If you went to do the integral now, you'd take that 12 out front. It's not that bad of an integral. Yeah? Then you'd multiply the y's. It wouldn't be horrific at all. I really want to focus on the decision making there, not on the I'll do what this question asks to do. Do not evaluate it. Questions there? So here's my decision-making structure. You can choose a different one if you want. My decision-making structure is draw a washer and pray that you can do it. And if it doesn't do it, then you're like, you do that whole body frustrated kick that my 8-year-old daughter's so good at, where it's like, oh, and then like, okay, here we go with the shells, But I'm not very good at shells. I'm worried about it. Then do some of the old questions that could be done another way. Do them with shells so that you get good at the method first. Yeah. More time here? Last one. Our job, decide, not do the integral. Decide and set up the integral. The solid generator will be revolving the region 4 minus x squared. Four minus x squared. That was horrible. How do you know this is 4 minus x squared? Well, you could sub in 0 and you'd get 4. You could sub in 2 and you get 0. I mean, hopefully 4 minus x squared is not what's going to hold you up here. Then 2 minus x. There's 2 minus x on both sides. Any Star Trek fans here? Sort of the Star Trek symbol there. It's a communicator we got there. This weird little, oh, let me shade it in for you if you can't picture it. There's the weird shape, and it's going to be revolved around the x-axis. When this is all, check out this weird shape. Oh, I'll do it with green on the bottom. No, green pen, silly rabbit. You guys even know what silly rabbit is? You don't, do you? It's sad. It's the Trix rabbit. They used to do these commercials. You don't care. All right. This is a weird solid. I like this solid. From the outside, it would look just like a football with a diamond-shaped thing cut out of the center of it. Making me wonder if there's another way to do this volume, but well, I'm not sure. If the x was negative 1, for 2 minus x, it would be 3, yes? Are you complaining that I missed the spots there?
The line equation, yeah.
2 minus x, when x is 0, it's 2.
Yeah, and when it's negative 1,
it should be 3.
2.
minus negative 1, yeah.
Minus negative 1 would be addition.
Oh, yeah. That's just the revolving, okay? The revolving's just messing us up. Let's just talk about in here. Yeah? 2 minus x, 2 minus 1 is 1. 2 minus 2 is 2. And the rest I just get from revolving. So this equation isn't 2 minus x over here. This equation over here is x plus 2. So that's the only part I'm drawing. And then the rest is by revolution, yeah?
Wait, what axis are we rotating this over?
X.
Okay. But if you were to rotate,
Maybe I don't disagree with you. Maybe they should have said y equals 2 minus x on the right side, and y equals x plus 2 on the left side. Yeah? Maybe they should have said that, yeah. I agree with you, absolutely.
okay.
Maybe even better. Maybe what they meant is, here, watch this. They just meant that stuff over there. Yeah? So maybe we should agree that this question is incomplete. You need some clarification. Maybe that's all they wanted there, was just about the positive x-axis. No. I'll say no. So let's do it that way. Does that take away the question as if we say for positive x values? Yeah? And in the positive side of things, okay? If you got the rest of the diagram, it's only going to change one thing in the whole question. The limits of integration. Because what I really want here is to draw the washer and hope, okay? So here's the washer. And this shading really helps to see the washer. Here's, oh, no, darker color for the washer. I always go darker with a washer. There. Do. And then the big one. Do. Can you sort of see the washer there? What I need is y values. Yeah, I got to take a y value and subtract the other y value. Do I have the y value? Can I solve for y here? I can. These are good. Oh, good. I can finish this off with washers. Who wants a shot at whether it's dx or dy, though? And how you know?
It's probably dx because looking at the washer,
Looking at the washer. Not until I look at the washer. Me personally, can I tell? And then you just draw a little depth on the washer there. Maybe that's how he did it. Do you think? He just colored it like that? There's the depth of the piece of bologna. This is a DX question. The rest is easy. I can do this by washer. I'm very happy. I don't have to do cylindrical shells. Okay, so volume equals A to B to, no, pi r squared. Pi, big R squared minus little r squared, dx. Volume equals, we're going to go 0 to 2. Not negative 2 to 2. Yeah, we need a little clarification here whether we want the other side of that solid, in which case we should have got another equation of a line. I agree with that. We'll just go 0 to 2. So it wouldn't be it would be this weird dome thing with a diamond cut out of the bottom of it. You know, when you looked at it, it would be solid. And then if you looked underneath, somebody's cut a little diamond underneath. So it fits on top of something else. Some engineering applications here. How are these shapes going to fit together as we build whatever we're going to build? Okay, pi out front. Outer radius is 4 minus x squared. Inner radius, 2 minus x. Big bracket for all that. dx. I'm actually not going to go any farther because I've made a mistake and I want you to catch it. It's my fatal mistake that I always make. I didn't square them. Oh, that is me. I always, even after all these years, I always forget to put those squares on there. Outer radius was the bigger graph, which was 4 minus x squared. Inner radius was the inner graph, which is 2 minus x. I'm subtracting those two, but the squared of those I'm subtracting. There's some multiplying out to do here and some collecting, some grade 10 type 11 algebra to do before you can start this integral, but it's not a particularly difficult integral once it's done. Ashley. Oh, no, it's not. This thing comes all the way around. In fact, the washer's showing you exactly where it's going to go. So maybe shading in the washer sort of helps here. At the end, after I got everything else straight in my mind, here's the washer. And that's exactly the path the shape follows, arching out that washer every single time. So every layer, that washer's in every single layer. You almost need the bundt cake again picture in your mind to go, each time that washer is every level of the bundt cake is a circle. If I cut the bundt cake this way, everybody would get a circular washer piece of cake with some depth, depending on what depth I did. And that depth is the dx. Yeah. Does that help? Experience is huge here, is that if the washer is vertical, if you're rotated around the x-axis, the washer will be vertical like this, and you're going to be doing dx's. For sure, there is experience that can help make these decisions. You don't have to rely on my pictures. Yeah, for sure. I like the pictures, me personally, because I'm like, I don't have to memorize a bunch of rules. I just walk up and draw it and say, there it is. Yeah.
Yeah, that's what I thought. So we appreciate.
Questions here? More time? It's a practice type stuff. This will hammer you. You'll get completely lost unless you've practiced a bunch of them. Yeah? I don't intend to be cruel on the test. I'll choose ones that are pretty reasonable, but you have to be able to make these decisions.